Hi, I'm Tim,
And I'm Nathan.
and our project is a recommender system for recipes. In this video, we will explain what a recommender system is, who uses recommender systems, the specific problem we've chosen, our implementation, and our results, including interesting challenges we faced, and our thoughts on further developing the model.
So firstly, what is a recommender system? As the name suggests, a recommender system typically gives users recommendations. In the era of big data, it's important for content providers to be able to sort through billions of items and recommend what you want to see. For example, Google's main source of income relies on its ability to recommend ads to the right people. Amazon has to recommend products, and Netflix has to recommend movies, and the list goes on.
For our project, we've chosen to build a recipe recommender system. Both me and Nathan are just starting out with this topic, so we've chosen to only optimize for accuracy. Specifically, we are optimizing for accuracy when predicting what rating a user would give a recipe. However, if you really want to be competitive with modern recommender systems, you have to go beyond this and optimize for diversity, serendipity, robustness, and other metrics like these so your users stay engaged and happy.
Our model is primarily based on a model called content-driven temporal regularized matrix factorization, which they call CTRMF for short. We wanted to explore the content-driven part of CTRMF, and so our model does not include temporal regularization. Temporal regularization essentially just adds biases based on time-dependent user information, like how frequent a user would rate a recipe and how recently they've been rated. So what is content-driven matrix factorization? First, let me describe what regular matrix factorization is. The goal of matrix factorization is to learn two matrices whose product is equal to the matrix of interest. In our case, the matrix of interest is a user-rated matrix which contains what each user has rated each recipe. Given this information, the MF model will learn what values to place in the learned matrices to generate a predicted user-rated matrix that is as close as possible to the real one. Content-driven matrix factorization is similar, but it decomposes the user-rated matrix into three matrices: a user latent feature, and recipe feature map. So the user latent and latent feature matrices encode relationships between users and features. The recipe feature map tells you whether recipe I has feature J by placing a 1 in the IJ index, if this is the case, and 0 otherwise. Therefore, we only use the features that are present in the recipe in the user latent and latent feature product. What are features? Features are information about recipes that contribute to how a user rates a recipe. For example, ingredients are a feature since the ingredient in a recipe is highly correlated with whether a person will like it or not. We also parsed out non-ingredient features from our dataset, such as how much time it takes to cook a recipe, how much equipment is needed, and so on. The dataset we use is a Kaggle dataset called FoodSysRec, which contains data parts from allrecipes.com. The data in this dataset was user rating info, recipe nutrition info, and cooking instructions. Our hypothesis was that content-driven matrix factorization will perform better than regular matrix factorization since this method uses content and collaborative information to learn instead of just one or the other.
Originally, we implemented everything from scratch with NumPy arrays. We actually got it to work, but training the model turned out to be really slow. It was so slow, in fact, that we were only training on about 1,000 user recipe pairs, but we had almost 300,000 pairs to train on. To add to that, everything was running on a CPU. Ideally, we'd want to parallelize everything and throw it on a GPU, but that required writing custom GPU code, and that just seemed like overkill. Also, our original implementation was using basic stochastic gradient descent with a batch size of 1. But in Waterloo's machine learning course, we learned about improved optimizer techniques like RMS prop and Atom. In short, our implementation wasn't good at all. Somewhere around the halfway point of the term, we decided to re-implement everything in PyTorch, which is a popular machine learning library. This gave us greater flexibility for testing and prototyping. With its auto-differentiation feature, all we had to do was implement the forward pass, and the update function would be taken care of. And to add some icing onto the cake, Parallelizing things on a GPU with PyTorch is very easy. The only hurdle was, how do we implement matrix multiplication using PyTorch? The forward pass, which predicts a rating given a user and a recipe, needed to multiply several matrices to get its prediction. The trick in PyTorch is that your learned values must be within the model's so-called state dict to be picked up for auto-differentiation. And adding basic tensors wouldn't get picked up into the state dict. But we found a little hack where you can just set up an embedding layer with the same dimensions as your matrix and just use the underlying weights tensor directly in your matrix computations. After that, we just set up a typical PyTorch training cycle using Atom as our optimizer and mean squared error as our loss function, and we performed our training.
We also implemented basic matrix factorization to serve as a baseline for comparison. We used the same dimensions for the latent feature space in both models, the same optimizer, and tuned the learning rate to achieve the best results. What we found was our model outperformed basic matrix factorization by quite a bit in terms of root mean squared error. The root mean square error of our model ended up being 0.814, and the root mean square error of the regular matrix factorization model was 1.416. To verify that our model was doing what we expected, we set up a small experiment. We identified 13 recipes that contained pork as the main ingredient. Then we created two users. User 1 rated all these recipes 5 stars, and user 2 rated them all 1 star. Then we identified 2 more recipes that had pork as the main ingredient and predicted the rating each user would give using our model and the regular matrix factorization model. As you can see, using our model, we predicted user 1 would rate both recipes at approximately 4.8, which is about 0.3 above average, and user 2 rated them approximately 2.3, which is over 2 below average. Regular matrix factorization was not able to predict an above average rating for user 1 and only predicted a slightly below average, approximately 0.5 rating for user 2. Although this is a small experiment, we believe this shows how strongly our model is at identifying user-feature relationships.
As this is more of an introductory project, we came across many ideas to spice up the model that caught our attention that were beyond the scope that we initially defined. First, there are visual and temporal aspects that influence the user's decision process when deciding which recipe they want to choose. Also, an ideal validation of our model would include testing with live users, and potentially splitting people into 2 random groups, one with basic matrix factorization and one with CTRMF, to see which one achieved better results in the real world. So to conclude, we talked about what is a recommender system, what are the internal workings of a recipe recommender, and our methodology, implementation, and results. Let us know in the comments what your thoughts are, and be sure to leave a like if you found the video interesting.